Hello, everybody, and welcome to the strong form of the pigeonhole principle. I believe that this is on page 25 of your workbook. Yes. Okay, so we're going to take a minute to talk through what this principle is saying. You'll recognize it as maybe sounding similar to the previous versions of the pigeonhole principle, but being a bit of a generalization of that. Okay, and I'd like to start by just filling in what this is saying, and then we'll actually write a short proof of it that might give us some insight into why this statement is true. Okay, so we'll start with the assumption that we've got a list of positive integers, q1 through qn. They can be any numbers as long as they're positive whole numbers. And what this form of the pigeonhole principle says is that if we put this number of objects in n boxes, and here's the number, q1 plus q2, and so on up to qn, minus n plus 1. If you put that number of objects into n boxes, then we get a kind of complicated sounding OR statement. Then either the first box contains at least q1 objects, or the second box contains at least q2 objects, or, and so on all the way up to the nth box contains at least qn objects. Okay, so basically what we're saying is if we start with this total number of objects placed into n boxes, then at least one of the statements on that chain of ORs has to be true at the end. Okay, so let's see if we can convince ourselves that this is a true statement that we have. And we're going to do what's known as a proof by contradiction here, which means that we're going to try to convince ourselves of this statement by demonstrating that if we assume the opposite of what it's saying, that can't possibly be true. Okay, so what we'll do is assume that we've placed this number of objects into n boxes, and then assume the opposite of what we're trying to prove. And just see where that leads us. Hopefully it will lead us to a contradiction, which will allow us to conclude that this statement is true. Okay, so we might start off then by saying this. Okay, suppose not. In other words, suppose the opposite of what we're trying to prove. Okay, well that would mean if we negate that big long chain of statements with all of those ORs, that would mean that the first box contains fewer than q1 objects, and the second box also contains fewer than q2 objects, okay, and so on until you get to box n, which is going to contain fewer than qn objects. Okay, that's the negation of what we're trying to prove here. And let's draw a picture of that so we can picture what we just wrote here. So I'm going to just write out and label the boxes. Okay, starting at 1 and ending at n here. And what we just said is that the first box contains fewer than q1 objects, so the most objects that it could contain is q1 minus 1, if it's fewer than q1. And similarly, box number 2 has to contain fewer than q2 objects, so the biggest number of things that could be in box 2 is q2 minus 1, one less than q2, and so on until we get back up to box n. That contains less than or equal to qn minus 1 objects. Okay, but then think about what that's saying. Okay, if we add up all of those objects, okay, then the biggest number of objects that could be in all of those boxes together would be the sum of all of these numbers that we just wrote down here. Let's write that down and see what that looks like. Okay, or another way of saying it, it's at most, the biggest possible number that it could be is the sum of all of those numbers. Okay, if we add those up, q2 minus 1, and eventually we get to qn minus 1. If we do the arithmetic there, notice what's going to happen. If we look at the q's first, we're going to be adding up q1 through qn. That's the first part of that. But then we're subtracting the number 1 n times. Here's a minus 1, there's a minus 1, and so on down to the n. Okay, and so what we've demonstrated as a result of our assumption is that this number here, that's the biggest number of objects that could be in all of the boxes together. But that contradicts what we assumed at the very beginning, that we've got a number that's 1 bigger than that in all of the boxes. And so we conclude then that the assumption that we made must be flawed. Okay, by assuming the opposite of what we're trying to prove, we've demonstrated that that opposite statement can't be true, and that proves that our theorem must be true. Okay, so we'll finish by just saying it this way. Okay, hang on a minute. Technical difficulties here. Okay, there we go. Contradicting our assumption that we really have one more object, okay, q1 plus all the way up to qn minus n plus 1. Okay, and that completes the proof of this result. Okay, and in a future example, we'll see if we can put this result to work for us.